Thank you to the organizers of the 2020 edition of Automated Software Engineering for the opportunity to present this keynote. It kind of scares me to say this, but I've been working in the field of software engineering for over 30 years, either as a developer or as a researcher. When you spend so much time in a field, it's easy to start thinking more inside the box than outside of it. In this talk, I'd like to step outside of the box and think about whether we, as a community, are truly addressing problems associated with the engineering of software. Now, on one hand, this is a rhetorical question. Of course, if we're software engineering researchers, by definition, we must be dealing with software engineering problems. Clearly, if you think about what it takes to engineer software, there's activities related to specifying the software, to designing it, to implementing, to testing. And if we look at the sessions associated with conferences like ASE, we'll see those kinds of themes and topics appearing in the sessions. Since software engineering researchers are the ones that are writing the papers according to those themes and topics, we must be addressing the problems of software engineering. But perhaps software engineering researchers are focusing too much on specific topics and not enough on what makes software engineering unique. To dig into what might be unique about software engineering, we turn to a description of software engineering by Randell. In describing how software engineering differed from programming, Randell describes software engineering as being about multi-person, multi-version development. This concise description captures much about what is unique about engineering software. Most software that requires engineering is big enough to require development by multiple people. And most software that requires engineering evolves and ends up with multiple versions. If we think about how software is developed today, this definition also captures the development of software from multiple components, each with many versions and written by many different people. For instance, consider the visualization of the development of TensorFlow created with Gorse. The visualization shows as nodes files that are created and changed in the system. The people who create and change the files touch and fly over the files. From this visualization, you really get a sense of the change, the multiple versions, and the multiple people who create software. Let's refine the question. Are software engineering researchers investigating multi-person, multi-version development? Let me summarize where we're going to end up with this talk. In short, software engineering researchers are investigating software engineering problems, but we tend to focus on a small number of topics at any given point in time, leading to a bit of a local maxima. I want to convince you there are lots of opportunities to investigate some unique aspects of software development around multiple person, multiple version development, and that by investigating these questions, we can develop approaches to improve both how software ecosystems evolve, as well as individual software development projects. Let's begin. To give you a sense of where the talk will be going, I've broken it into 4 sections. We'll start by digging deeper into what problems software engineering researchers are addressing. Then we'll take a look at work that touches multi-person, multi-version development, first in terms of software ecosystems, and then at the individual project level. Based on these investigations, we'll consider what is missing for the field to make more progress on asking and answering questions about multi-person, multi-version development. Let's start by considering what problems are being addressed, and to do so, I'm going to call on the help of an avatar named Sally. In thinking about the question, Sally has to consider how to actually study what it is that software engineering researchers are spending their time on. There are at least 3 ways the question can be studied. First, software engineering researchers could be interviewed and be asked to describe their recent projects. Second, a survey could be developed to ask researchers to respond to questions asking about problems or areas being studied. Third, software engineering researchers record what they're studying through the published literature, so the software engineering literature could be analyzed. Sally knows there are pros and cons to each of these approaches. In brief, Sally is considering how broad the inputs are to study versus how deep they are. A broad set of inputs provides more generalizability of the results. A deep set of inputs can provide more understanding of characteristics of the work. When Sally thinks about the approaches, she recognizes that interviews provide deep information about what software engineering researchers are studying, but it would likely be hard to conduct many interviews, likely leading to less breadth and less generalizability. When Sally thinks about surveys, the information is broad, but not likely as deep. For the questions posed in the survey, generalizability of the results might be gained, but it may be hard to consider aspects of research that weren't conceived of when the survey questions were created. When Sally considers the literature analysis option, she finds a balance in the breadth and depth of inputs and analyses considered. Reviewing published papers, the literature, allows a reasonable view of the cross-section of software engineering research, depending on the publication venues considered. It also provides a reasonable means of considering different aspects of the research based on the in-depth descriptions that appear in the papers. Of course, Sally does see drawbacks. The work not selected for publication is not represented, so biases in the community are reflected. To answer the question, Sally suggests focusing on the literature. Let's consider first existing work that has analyzed the literature. Here is Sally's quick synopsis of two existing published studies that perform an analysis of the literature related to the question of what problems are software engineering researchers studying. 2006, Card and Kai analyzed 540 papers that appeared in 7 journals and conferences that year. Their analysis considered which of 15 software engineering topics the papers addressed. They found that 77% of the papers focused on only 20% of the 15 subject areas. The topics most frequently appearing were testing and debugging, software program verification, and management. Matthew and Menzies later analyzed over 34,000 papers that appeared in 34 software engineering venues between 1992 and 2016. They considered the popularity of topics over time. They found that topics ebb and flow over the years, with topics such as source code, program analysis, and testing rising in popularity to 2016. Sally recognizes that this focus can be beneficial. Focus can enable a community to make significant progress on a particular topic in a short amount of time. However, focus can also have a negative side. Too much focus may mean that there are interesting and important problems that are being overlooked. Is too much focus on too few topics causing the software engineering community to miss opportunities to address interesting and important questions? What about those unique aspects of software engineering outlined by Randell? To dig into whether or not we as a community are addressing aspects of multiple people and multiple versions in the problems and solutions about software development that we're studying, I analyzed 276 papers from 3 conferences in 2019. For each of these papers, I took a look at the abstract, sometimes parts of the body of the paper, to assess whether or not the paper addressed multiple people, multiple versions, both of those aspects, or neither of them. I took a conservative stance in this analysis, assigning the attributes if there was any indication that the paper addressed them. To give you a glimpse into this analysis, I'm going to show you 3 different papers from ASE 2019 and show you how I characterized them. Apologies to the authors in advance if I mischaracterize their work in any way. Here's the first paper. It's a paper about identifying controversial posts on question and answer sites like Stack Overflow. Given that Stack Overflow brings together the wisdom of multiple people, I assigned it the multi-person attribute. Here's a paper that recognizes that there are challenges in trying to do performance testing at every revision of a system. If you have a system like Python's NumPy, which is used in TensorFlow, you might take the cost of running performance tests frequently. But in many cases, you're not going to do that. And so this paper took a look at whether or not you could build a model and estimate when you should actually run the performance tests across different revisions. And as a result, I assigned it an attribute of multiple version. The third paper creates a model of source code token embeddings to help with a variety of development tasks, including assigning code authorship and detecting code clones. When assigning code authorship, that's a problem that deals with multiple people. When detecting code clones, that typically happens across multiple revisions of a system. I thus conservatively assigned both tags to this paper. Let's take a look at the results of the analysis. As you can see from the pie chart, there's very few papers, only 1%, that were assigned both attributes of being about multiple people and multiple versions. We had a few more papers that were one or the other, but clearly there is a lot of opportunity to investigate various aspects of multi-person, multi-version software development. To sum up this section, of course software engineering researchers are addressing software engineering problems, but analyses of the literature repeatedly shows that as a community, we can narrow in on a particular set of topics at different points in time. Narrowness and focus can bring progress, but I contend they can also cause us to be finding good to great solutions for only certain kinds of problems, while ignoring many other important issues. In particular, we very well may be understudying important aspects of what makes software engineering unique. Brian Randell aptly and concisely recognized that multi-person and multi-version development separates software engineering from programming. Perhaps as a community, we could do more to consider problems and solutions more centered on these aspects. In particular, perhaps it might address some of why what we study in software engineering research can be seen as far from the problems faced by practicing software engineers. I'll come back to that point at the end of my talk. Next, I'd like to expand on what kinds of multi-person, multi-version questions arise in each of software ecosystems and software projects. Let's first look at software ecosystems. I'll use the term ecosystem to refer to a collection of interdependent projects, such as you might find for Java or Ruby or Node.js, where applications and libraries rely upon each other to deliver functionality. These projects might be stored in a repository such as GitHub. A software ecosystem involves many different individuals working on many different projects. If we think about what kinds of questions might be interesting to ask about multi-person aspects of the ecosystem, they might include these ones, but I'm sure you're going to have other better questions. If we then shift to consider that software ecosystems include many versions of many components and applications, what questions come to mind that might help us improve the overall evolution of software ecosystems? Here's a few that come to my mind. What questions come to your mind? Of course, these questions aren't entirely novel. Aspects of these questions have been studied before. I've listed some pointers to papers that have described research related to these questions. You'll be able to find the resolution of these references at the end of the posted slides for this talk. And what questions come to mind if we consider both multi-person and multi-version aspects of the evolution of a software ecosystem? Within a software ecosystem, there's supply chains of interdependent software components where one component relies upon another. In real physical supply chains, say for the parts that make up your phone, there's going to be some sort of relationship, financial or otherwise, between the client and the supplier. Apple has deals to buy components for your phone, for instance. In software, those relationships between the people building the components may not exist, and a component owner may not even know how many downstream other components it relies upon. An even simpler question than asking for optimal length of supply chains is whether there's a need to be able to visualize and analyze supply chains. Similarly, we can ask questions about what attributes teams might need or compositions of teams might need to build high-quality components. High quality might be where there aren't security vulnerabilities or some similar characteristic, and it might be useful to know if there is more overhead to use one component or another similar component? Software development teams often have to ask these kinds of questions as they decide upon which open source component to use. Let's consider these questions both in terms of studying trends in software ecosystems, as well as studying examples of particular software ecosystems. Let's start by considering trends that were identified by Sonatype and partners as part of the analyses they conduct for their annual State of the Software Supply Chain report. I'd like to thank Derek Weeks and Sonatype for allowing me to present some of their material. Their data shows that multi-version software is simply a reality. Over about a 2-year time period between 2018 and 2019, the number of releases of software components in public repositories increased 75% to being about 28 million components that were available. These components had many releases. On average, developers had access to more than 21,000 releases each and every day. Now, in order to conduct their analyses, Sonatype created a data set. They started with all the components that were published in the central repository, and then filtered down looking for components that had at least 2 version releases in the last 5 years, and that had a certain number of dependencies. They ended up with a data set of about 36,000 components, which are the basis for the results that I'll show you here now. One of the characteristics that they considered in depth was the time to update. This refers to the time it takes developers to upgrade their component to a new release of a dependent component that they may be relying on. Let's look a little bit at the definition. Here's component C. It's in release 2.2, and it depends on both component A and component B. At some later time, there are new releases that are happening of A and B, and it's not until component B upgrades to 2.3 that the developers of component C decide to upgrade the dependency. The time it takes from the release of components B version 2.3 to when component C updates to that new dependency is a time to update. Similarly, we can look at the time to update to component A. Now, there's various questions that we can ask about multi-version, multi-person development. Do components with more active developers correlate with faster mean times to update? Through their analyses, Sonatype was able to determine that the top 20% of teams by size actually had quite a substantially faster mean time to update and actually released their software more frequently. Another question that we could look at is whether components with higher release frequency and higher monthly commits end up having a faster mean to update. And indeed, the top 20% of teams by commits per month had much faster mean times to update and faster release frequencies. This provides an interesting trend analysis of what happens in software ecosystems that deal with multi-version, multi-person development. The size of the team can actually help you do more frequent updates and thus perhaps be less vulnerable to things like security vulnerabilities that might be being fixed in new releases. Now, there's a lot of questions that we had posed about multi-person and multi-version development. One of these was actually looked at by the Sonatype team. They developed an idea of what an exemplary development team might be, and then they looked at various metrics that correlated with those teams. And you can see that some of the factors that actually lead to high quality components are having a larger development team and being really fast to update dependencies. These kinds of results can help development teams understand that frequent releases are actually a really important characteristic to strive for. While the Sonatype investigations consider both multi-person and multi-version aspects of development in an ecosystem, the investigations are heavy on the multiple versions of components created. Mark Palyard led work that also investigated multi-person and multi-version aspects of development in an ecosystem, but where the emphasis was on how multiple people interacted across the multiple versions created. I'll briefly recap this work as another example of how we can consider multi-person, multi-version aspects of software engineering. Mark's focus was on the social interactions occurring in software ecosystems, the when, how, and why of those interactions. On the right side of the slide, you can see 4 components: Selendroid, OKHTTP, Netty, and Alto XML. The solid lines show the technical dependencies between these components. We know that developers in an ecosystem also interact, and that developers sometimes interact when they use a component, such as when they file a bug if they find a problem. You can see on the slide that a social interaction or a social link is indicated between OKHTTP and Netty. The results I'll present are based on analyzing these technical and social interactions on a selection of projects from GitHub. I'm going to show you results from pairs of Maven projects. The results from the Ruby ecosystem were similar. First, let's consider when social interactions occur. The x-axis of this graph shows the number of user projects depending on a component. The further right in the graph, the more users of the component. The y-axis shows the ratio of user projects of a component that have social interactions. The higher in the graph, the more social interactions between a component and its user projects. Each red dot represents one or more components in the analysis. The size of the red dot indicates how many components are plotted at that location. The top band of the graph includes components for which there are often social interactions with user projects. The second band of the graph has components that have social interactions only some of the time. The component with the highest number of involved user projects is Vault, which is related to the video game Minecraft. The ratio of user projects socially interacting with the component is high because, by convention, user project contributions are also provided to the Vault component. The last band has components that rarely have a social interaction with user projects. Popular projects like JUnit are used by many others, but users typically don't need to socially interact with JUnit to make use of it. This analysis of the social interactions in the Maven ecosystem demonstrates that the more popular a component, the less likely it is that developers of a user project will need to get involved with the project on which they depend. In addition to knowing when social interactions occur across the ecosystem, we also wanted to understand how social interactions occur. The visualization on the screen represents the data we're interested in. The row represents a pair of projects, a component and one of its user projects. Each icon represents an instance of a social interaction, with different icons representing different kinds of interactions, such as the addition of a comment to an issue or a commit. Icons that are dark originate from a developer on the component being used. Light icons originate from a developer associated with the user project. The red line indicates when a technical dependence was added from the user to the component project. In this example, the light icon on the left side of the red line indicates a social interaction preceded the introduction of the technical dependence. In this case, the user project sent pull requests with a needed feature to the component project before adding a dependency on it. There are also instances of the technical dependence introduction preceding social interaction. In these cases, a user project may initiate a bug report only after depending on the project. In our analysis, we considered trends across all the project pairs. The violin plot on the left side of the screen compares the distributions of when social interactions preceded the introduction of a technical dependence and vice versa. We can see from these plots that when the technical dependence occurs before social interactions, the number of social interactions between the two projects is typically small. However, when the social interaction precedes the technical, there are many interactions, which may be an indication of a strong community. The third set of questions we posed were around why social interactions occur. We randomly selected 50 pairs of projects from each of the Maven and Ruby ecosystems and qualitatively assessed why social interactions occurred. The table on the screen indicates a few of the reasons for why social interactions occurred between user and component projects. We were expecting the forward situations where a developer of a user project files a bug report or a feature request with the component project. We were not expecting to see backward cases. where a developer on the component project initiates a social interaction with developers of a user project. For example, we found cases where the developers of the component project help fix a bug on the user project through a pull request, or help the user even use the component. These results show more interaction in the ecosystem than we expected, and can provide insight for developers in the ecosystem of what kinds of overhead to expect when using a component. For instance, if a developer had a choice between two similar components, knowing how much overhead there might be in using one may help the developer make a choice. The kinds of analysis possible about multi-person, multi-version development in software ecosystems helps identify trends that can help characterize properties of software and properties of development in that ecosystem. As demonstrated through the sonotype analysis and the analysis of social interactions, these analyses support answering interesting questions for development teams, such as how fast to update a component dependence and how to assess how much interaction might be needed when adding a dependence to a component. Let's now consider what kinds of multi-person, multi-version aspects can be analyzed for individual projects, and how consideration of these aspects might aid the development of a particular project. As we saw, ecosystem analysis of questions about multi-person, multi-version development can provide insights to individual projects. For instance, release velocity is a positive indication of how well teams perform, so an individual project may want to benchmark itself against the release velocity happening in an ecosystem. In this section of the talk, we're going to focus in on an individual project and take a look at what kinds of questions we might be able to ask and answer about multi-version, multi-person development for individual projects. Imagine you're a development manager. Perhaps you might want to know whether or not the process that you're using for development is efficient, or how you can improve efficiency. If you're a developer, perhaps you'd like to know how long it's taking to actually define and deliver a new feature, so that you can understand whether there are ways to increase the delivery of new features in your project. We're going to use an example from Moodle. Moodle's an open source learning platform. We're going to look at a particular feature as a way of thinking about the questions for multi-person, multi-version development. The feature we'll look at is named ASE2020, and it's about adding an ability in the open source platform to be able to request donations and do that in a campaign style. Moodle defines its new feature requests as a kind of issue. Here's a little view on the history of the development of this particular feature. On April the 2nd, the new feature issue was created by developers whose initials are SB. Over the next couple of weeks, there were refinements to the feature definition by both SB and a new developer, AN. A little while later, a new developer, SL, picks up the issue to actually work on and does the implementation using a continuous integration bot to test. There's a number of events that happen during the life cycle of this particular feature request, about 60, and you're seeing just an abstraction of a few in this particular view of the issue history. What's interesting is it really is multi-person, multi-version development. To be able to build this fairly simple feature took about 10 different individuals that had different roles to play in the development. It took about 2 months and 6 days to actually go from the start of the feature definition to the feature being delivered. We are back here with Sally to consider another view of this flow of work on a feature request for Moodle. Let's consider the work on the feature as a flow of events. Work starts with the creation of a new issue describing the feature by SB, who's up there in the corner. SB initiates the feature request on April the 2nd. The initiation of a feature request can be considered as activity related to specifying the software being built. Let's consider this event and its corresponding work as being classified as a specification activity. In associating the event and its work with the specification activity, we can record the event and its data with this bubble representing specification. The data may include the issue, including who created it and when, as well as the time spent creating the feature request. We'll represent this recorded event and its data as a black dot in the specification bubble. A bit later that day, SB has thought more about the new feature and updates the issue with new information. These updates can be added as a new event with associated data to the specification activity bubble. At this point, our abstract representation of the development of this new feature has seen two events, both of which pertain to specification. Almost a month later, another event occurs when a developer whose initials are BR adds comments to the issue about the design of the feature. We associate this event with another kind of development activity depicted by the design bubble. We associate the event and its data with the design bubble. At this stage of development, we have seen events and work occur related to specification and to design. The ordering of events allows us to represent the design event as occurring after the specification events by using an arrow from specification to design. As development progresses over time, more events will happen and can be associated with different kinds of development activities. Let's fast forward and see a representation of what the development of this feature request might end up looking like. Here is a representation of the overall development of MDL68320. You can see that for this feature, development was quite linear, from specification through to testing. If I had gone through and labeled the events really carefully, it's likely there might be some additional iteration between implementation and testing, but it was minor. The labels under the bubbles indicate how much time was spent by different developers on each kind of activity. You can also imagine gathering data to indicate where developers were waiting, who they were waiting upon, and how long they were waiting. With this kind of representation, we could start analyzing where time goes. If we represented the development of multiple features in the same way, we could start to see trends for an individual development tree. We could analyze the aggregate information using queuing theory or other similar approaches to dig in how to improve the development process. This kind of analysis is not really any different from what has happened in physical manufacturing plants as part of the lean movement. Lean manufacturing came from the Toyota production system introduced by Taiichi Ohno. This system and approach maps the value stream, which describes how a product or service goes from initiation to its final product. When the value stream is understood, efficiencies can be introduced. A very visible and well-known application of value streams is the production of cars, where manufacturing lines are honed to be as efficient as possible, both in the design of the stations used to perform an action and the flow between stations. The value stream maps used in manufacturing are a special kind of flowchart. You can see a fragment of a manufacturing value stream map on the screen. It describes various welds that are going to have to happen in the factory and the time it will take for each weld. The idea of value stream maps has also been applied in software engineering. Poppendijk and Poppendijk were some of the first to describe how you might sketch out a value stream map for a software development process like the delivery of a new feature. They describe how you might then take that map and, if you were going to adopt agile approaches, how you might modify that value stream map to be more agile in your software development. Value stream maps have also found some traction in industry. Ben Ali and colleagues have described their use at Ericsson. They mention a number of challenges that they faced in trying to apply value stream maps in software engineering, such as the need to capture information flow, the need to connect the pen and pencil sketches that individuals might make to actual data, and overall, the need to analyze and visual value streams that are occurring for software development. Mick Kirsten, who I've worked with for over 20 years, has a book that explores the treatment of software development as a value stream. Mick's thesis in the book is that many business sectors are currently undergoing major transformations, and that a focus on the end-to-end software value stream is necessary to enable a correlation to business outcomes. Mick's observations come from thinking about flow for many years, starting with his PhD work on the task-focused interface, which manifested in the Eclipse Myelin tool. Mick and I co-founded TaskTop Technologies with the goal of enabling better flow in the programming part of software development. As we worked with more and more companies, we saw the need to think about flow beyond the IDE. In addition to enabling flow within the IDE, TaskTop began to focus on connecting the world of software delivery by connecting the many best-of-breed tools used in software development. As TaskTop has gained more and more insight into how software development occurs at our customers, the need to truly enable end-to-end value stream flows tied to business outcomes has become apparent. In his book, Mick outlines what he calls the flow framework to enable end-to-end views and analysis. The flow framework includes several layered models. I won't have time in this talk to go through the entire framework, but I wanted to point out to you the flow metrics introduced by the book. The flow metrics help a development project answer some of the questions I posed about multi-person, multi-version development of individual projects. For instance, flow time for a feature request would be the time it takes a feature to go from specification to delivery. Computing flow metrics like flow time for development projects is not always straightforward. In many proprietary settings with large development teams, there can be many different individuals playing different roles using different tools. Here is an abstract view of the kinds of development team configurations that happen in practice. You can see the kinds of roles of team members at the top of the screen, ordered roughly from value initiation to value delivery, with stakeholders and analysts on the left and the customer on the right. In between, we have the architects, project managers, developers, operations, support desks, all roles that are needed to create and deliver the desired value to the customer. You can see titles of groups of tools, such as planning tools, tools for building software, continuous integration operations, the ability to do support, and others. Each blue rectangle is a kind of tool used for a given step in the value stream, with each white rounded rectangle a different kind of artifact used to represent a flow item. The arrows indicate how information flows between the tools. To compute flow metrics and answer questions about multi-person, multi-version development for a project, you need to be able to follow flow items, like feature requests, through these people and tools, just like you can follow an individual car through a manufacturing assembly line. TaskTop has technology that enables following the flow of items, which enables the computation of flow metrics. Here's a view of flow metrics computed for different value streams at TaskTop. The metrics give insight into what the developers of different value streams are working on through the flow distribution. For instance, at a glance, one can identify whether a team is working on many bugs in a sprint, shown as red, new feature requests, shown as green, or technical debt, shown as orange. One can also see more detailed metrics such as flow velocity to see how long it is taking to complete individual items of work across all the people and tools involved. This visibility of value streams enables tracking of the status of value streams, benchmarking of a value stream against others, as well as other insights. In summary, in this section, we've been looking at how we might consider more aspects of multi-person, multi-version development at the individual project level. We've seen how thinking about development as a value stream can provide new opportunities to understand, manage, and optimize software development. In this last section of the talk, let's consider some of what is missing to be able to investigate multi-person, multi-version aspects of software development, particularly at the project level. To sum up what is missing in one image, we need to mind the gap and try to fill it. What gap am I referring to? The gap between how proprietary software is developed and the information in those proprietary developments it's possible to determine compared to open source development. I showed you an abstract diagram about the kind of information flows that happen in proprietary software development projects where there's many people and many tools involved. In fact, TaskTop has studied hundreds of such tool chains that happen in proprietary software development. You can see snapshots of some of them on the screen. What I want you to take away from these views is that there are a lot of tools in use and in order to create a value stream, information needs to flow between them. While in many software development teams the information flow between these tools is manual, there is increasingly integration software, such as that provided by TaskTop, to automate these flows. When the flows are automated, they can be traced, and it becomes possible to look at questions about flow in the value stream. In open source development, on the other hand, this traceability of information can be more difficult. For instance, there's a tendency to use fewer tools for more purposes. The issue tracker becomes the home for not only bug reports, but also new feature requests. This can lead to inconsistent capture of the information needed for the task to be worked upon. We also see an intermingling on the few tools used of information from different development activities. For instance, on the issue we looked at for Moodle, that I've been using as an example, some comments in the issue pertain to defining the feature, other comments pertain to the design of the feature, and still others record implementation and testing activity. To be able to analyze aspects such as flow of development, we need to distinguish what information belongs to what activity. Giovanni Vivani, a PhD student in my group, has been working on how to identify design information in such comments as one step towards disambiguating which activity information belongs to. A promising approach is determining ways to leave breadcrumbs as part of the development activity. Where can we introduce automation that helps developers at the moment, but also leaves a breadcrumb about the development process? Many such aids already exist. For example, there are Git hooks that help link commits to issues based on naming conventions. One might imagine a bot in Slack that recognizes a question is about design and is able to then track and initiate the tracing of who answers the question and how long it takes. If we had enough of these kinds of breadcrumbs, we could better piece together development flow without requiring open source developers to use more tools or follow a prescriptive, detailed development process. The key here is to think about where valuable information about development flow can be gained, and to focus in on how to automate some aspect of the flow. As we automate different steps of the process, and they might be automating micro steps as through Git hooks, we need to connect the information together to be able to observe likely flows. The automation and connection of automated information will be possible if we always keep our eye on providing benefit to developers. So in summary, what's missing? Well, in my view, we are seeing an increasing gap between what is possible to study in terms of some important aspects of multi-person, multi-version development and proprietary systems that are next to impossible to study in open source development. If software engineering research is going to take part in these important questions, we either need to do much more work with proprietary software development teams, or try to nudge open source projects to be able to identify and track some crucial information. Automation could help in improving our ability to investigate some questions in open source. Before I wrap up, I would like to say thanks to the many undergraduate and graduate students, postdocs, and colleagues, both at UBC and throughout the software engineering research community, who've contributed to how I think about software engineering and research today. To Mick Kirsten and my colleagues at TaskTop, thank you for the many great discussions, collaborations, and insights. And to the organizers of ASE 2020, thank you again for the kind invitation to present this talk. In this talk, I've asked the following question: are we, as a software engineering research community, truly addressing problems about the engineering of software? We took a look at some existing literature. I reported on an analysis I had conducted of papers published in 2019, and found that perhaps we got a little bit too focused as a community on a few topics at any given point in time, and perhaps there's more opportunity to study some unique aspects of what makes software engineering special, namely that it's about multi-person, multi-version development. That's not to say that there's not a lot of great work going on. We saw examples of ecosystem analysis that can help identify useful trends, such as releasing frequently can lead to better outcomes. Ecosystem analysis can help individual projects, but more opportunities exist for looking at multi-person, multi-version development in the context of individual projects, particularly around information flow and value stream management. And finally, we took a look at the gap that exists between the kinds of information available for proprietary software to look at information flow and what's available in open source. I hope I've convinced you that there's some opportunities for automation that might help us enable more study of these characteristics and this kind of problem within open source systems. So is software engineering research addressing software engineering problems? Of course it is. There's many great examples of software engineering research results that are making a real impact in practice today. But I hope I've also convinced you that there are opportunities out there to investigate multi-person, multi-version development to really improve both software ecosystems and individual software projects. I hope we as a community can step out of the box we sometimes put ourselves in and take a look at problems that deal with this unique aspect of software engineering. Thank you.